further ado, Dr. Marty Simon.
Thanks. It's an honor and a privilege to be here. I appreciate the invitation. It was extended last year and we couldn't quite work it out, so I'm glad it worked out this year. I'm going to talk about some stuff today that will, well, not entirely, but a significant part of it I haven't talked about before. I haven't published yet. So I'm hoping for some tough questions and some good discussion. Basically what I'm going to do is I'm going to give you a little background on the research program that this is part of, we call Learning Through Activity. I'm going to talk a little about reversibility, what we mean by it, and its importance. Then I'm going to share with you something that I haven't shared before, which is our typology of reversibility. And then if time doesn't run out, I will talk a little about fostering reversibility. But I want to leave time for discussion, so at a certain point, wherever I am, I'm going to stop and open it up for discussion. So there's an ongoing research program. It originally started as part of another research program, and then there have been 2 grants supporting this program so far. The goal is to understand abstraction through activity, abstraction that comes through a learner's activity, and how to promote it. And the basic idea is that if we look at kids, both in and outside of instructional settings, they seem to make some pretty powerful abstractions based on their activity. So for example, a kid who doesn't have a concept of number can engage with a parent, for example, in counting things. And originally that counting thing is just learning the song, 1, 2, 3, 4, 5. Eventually they learn to say a number and touch something at the same time. They still don't know what 1, 2, 3, 4, 5 means. It could just as well be A, B, C, D, E. But through that activity, somehow, they come to have an understanding of number. They come to understand that if I leave off at 4, that describes something about how much stuff there is. And 6 is more than that, and so on. So if kids are learning through their activity, then the basic idea is we should be able to understand how that works, and we should be able to promote that. That is, we should be able to design for students to be able to use the appropriate activity and develop an abstraction from that activity. And so that's what we're about, and you'll see more of that as we go on. So this is based on the notion of reflective abstraction. Unfortunately, when people talk about reflective abstraction, it's usually that something is the result of reflective abstraction. And we don't really unpack the process of reflective abstraction. So if they're here now, there must have been a reflective abstraction. So that it's not very descriptive of how it came about. And if we don't know how the transition came about, we're not that well empowered to foster that transition. So what that implies is that we're interested in studying the learning process, not just the landmarks of knowing. So a lot of people who describe what they do as studying learning, what they're doing is saying learning proceeds through these steps. The student understands this, and then they understand this, and then they understand. And this is important work. I'm not minimizing it in any way. We need to know kind of what the landmarks are. But then our question is, so how do you get from one landmark to the other? Because it seems to me teaching at its best is the promotion of those movements from one landmark to the other. So we need to understand that transition. This is sort of captured by Rena Hershkowitz's comment. in spite of the animated theoretical debate that has taken place on the nature of abstraction, little experimental research is available. We surmise that the lack of experimental evidence is due to the difficulty of observing the process of abstraction as opposed to the products for which there is more evidence. So how do we go about working on this? Well, because we're particularly interested in students' activity and how they make abstractions from their activity, we're trying to, one, be able to pay attention to that, and two, minimize the impact of other factors. Okay, so this is not about observing them in the natural setting of the classroom. It's about trying to create a condition, trying to create ideal conditions for studying this in a very intensive way. So we work in one-on-one teaching experiments. And the reason we work in one-on-one teaching experiments is because when a student is listening to somebody else's explanation or watching somebody else do something, we no longer have a trace of their activity. There's probably mental activity going on, but we don't have anything visible or auditory to pay attention to. And so we lose that trace. So what we do work with one-on-one with students so that we have a constant trace of them doing things and saying things. And they're never in the passive role where we have no indications. We use task sequences that are designed to build from activities that they have available, and those are constantly being modified in the context of an ongoing analysis of these teaching experiments. And the role of the researcher is limited. The researcher doing no coaching, no demonstrating, no hints, and no leading questions. Ideally, okay, we slip up, but that's what we're trying to do. And again, it's because if there's a change in the way a student's thinking because we told them what to do, or we made a suggestion, or a hint, or a leading question, then we've lost what we were trying to pay attention to, which was just how things proceed based on their activity. We learned all this stuff the hard way, by the way, which is the original grant we were to work on this. We were going to use other people's data. And we went to several places, including coming down here to meet with Les and look at some of his data, and realized that we had to collect our own data because we wanted something very specific. We didn't want the two kids talking. We had a problem when the two kids were talking to each other. One kid was talking, the other one was listening. We had a question. We had a problem when the interviewer was asking leading questions or making suggestions, and so on. There were just too many features that were making it very difficult to do this already difficult work of paying attention to the learning process. So after making 2 or 3 different visits to different places with the idea of working on other people's data, we went back to NSF and said, okay, we got to change the project entirely, and we collected our own data. By the way, I was going to say this later in the talk, but I sent Kevin 2 papers that describe this in more depth, the Learning Through Activity program. So if you want to read more about it, Kevin can share those. I know he shared them already with his team and Les's team, right? So what this is a teaching experiment where the spotlight is both on the instruction and the learning. If you think, for example, of something like Les's teaching experiments, the same cycle is going on, which is that when you analyze the learning, it affects what you do next, which affects the learning again, and so on. But the focus is all here. Okay, there's no very conscious focus on how are we fostering the learning. Okay, they're trying to pay attention to the students' mathematics, the different steps they go through, and so on. What we're trying to do here is look at this together. Okay, so we're shining the light on on all of this, so that we're continually trying to understand the sequence that promotes the activity and the reflection on the activity and the resultant abstraction or the lack thereof, and so on. So our approach, which I'm going to describe in more detail, is in contrast to a couple things that you see a lot of in this country anyway. One is what we might call a problem-solving approach. And in a problem-solving approach, typically, a problem is posed to the students in which, so first of all, what's not up there is sort of a traditional approach where the teacher tells the students what it is they're supposed to learn and shows them what they're supposed to do. Okay, and when we decided we didn't want to do that as our primary means of instruction, it created a bit of a vacuum, and certain other things have sort of moved in to fill that vacuum. One of them is this problem-solving approach, and I'm not saying anything against either of these. All I'm saying is I want you to understand how what we do is different. So in a problem-solving approach, a problem is posed that requires some of the mathematics that we want the students to learn. Okay? And it may be that nobody can solve the problem. It may be that a few people can solve the problem. It may be that a lot of people can solve the problem. But that's the context for it, and then it usually moves to a classroom discussion in which people share their solutions and so on. So whether one sees the learning here or here, the learning takes place either through having to make a problem-solving, I'm going to say leap, okay? In other words, that there's an uncertain step of whether you can solve this problem. You don't know this mathematics yet, and so it's not clear whether you're going to be able to solve this problem or not, right? And if you don't, then the idea is that you will get it through the discussion, people talking about the ideas that are to be learned. Okay? What we're doing is very different than that. We're trying to promote activity that the students already have available. So if we do this in the ideal way, they never encounter a task that they can't solve. Okay? We're always giving them a task that they can use available activity to solve, and it's through that they make their abstraction. I'll show you that. That probably sounds really weird to you. Okay? Now this is not a model for doing every bit of mathematics instruction. Okay? This is a potential instructional tool that hopefully allows us greater power in helping students develop some of the concepts that they don't readily develop. Okay, some of the more difficult concepts that they don't develop, that there's a way to engineer for learning those concepts. We don't ever want to have mathematics instruction that it doesn't involve problem solving. Okay, so this is a complement to it, not an alternative to it. Oh, I meant to say at the beginning, if I say something that's unclear to you, please ask me on the spot. It's much better to get the clarification in real time. If you have discussion, we'll hold that to the end. But anything that I can clarify what I'm talking about, please ask. Okay, so we're designing for development of an abstraction. So first of all, we're focusing on a single abstraction. We're not trying to promote a whole complex of abstractions or complex of ideas in one fell swoop. In other words, we're coming up with a trajectory that sees a single abstraction building on another single abstraction and so on. We talked about the next one. Basically talked about the other one. So it's always trying to figure out what activity does the student have available that they can use to learn something. Okay, so in the example of the kids counting, they had the activity of being able to say the word and point at the object, right? And they used that to, I would argue, reflectively abstract the idea of one of those numerals as being a number that represents the manyness of the set. So let me give you an example so you get a feel both for what we do and what we mean by a single abstraction and how it comes about. So we're talking about a fraction of a set. So there's a fraction of a quantity. You could think of it as a composite unit, and the results we're talking about are whole numbers. So an example of that would be 5/7 of 35, and we have our fourth or fifth grader. I can't remember whether this was from her fourth grade year or fifth grade year. Kylie, who we give this pre-assessment right before instruction, and she doesn't have any idea how to do that. So then we give her a task. Here's a bar. It's 10 units long. Show me 3/5 of the bar and determine its length. So Kylie cuts the bar into 5 parts, pulls out 1 part, iterates it 3 times. So if you're familiar with Java bars, and I cheated, this is actually, I used fraction bars, not Java bars, to create the picture, which is a next generation of Java bars. So basically, she started with a blank here, a blank rectangle, cut it up into 5 parts, pulled 1 out, and then iterated that part 3 times. And said this is 3/5 of that. Okay, and remember the original bar was 10 units long. And I said, how long is the new bar? She said, it's 6 units long. Explain that. I cut it up into fifths, and if you want to know how much each piece equals, 2 units. How do you know? 2 times 5 is 10. What's the 5? How many pieces I cut the unit into? What's the 2? The number of units in each piece. How do you get 6? I looked at each of the pieces and counted by 2s, or 2 times 3 is 6. Okay? So what she is doing right now is she's using 2 activities she has available. One, she has the activity of creating a non-unit fractional bar from a unit bar, right, by partitioning it, pulling 1 out, iterating the part. And 2, she's using her whole number multiplication and division to evaluate the size of those pieces and ultimately the size of the new bar. No abstraction has been made yet. There's no claim of any learning yet. Okay? She's doing this task using the activities she already has available. If she couldn't do this task, then our design isn't right yet. And we need to figure out where she is now and how to design for her to learn the things she needs to learn so that she can do tasks like this. Then she's given a similar task as a bar. It's 18 units long. How many units long is 2/3 of the bar? Okay, and we're also starting to drop out the specific directions of draw the bar or find 2/3 of the bar. Kylie cuts the bar into 3 parts, pulls out 1 part, iterates it twice, and provides a similar explanation. Okay, and each of these problems, I can't remember whether these are successive problems. There probably leaves some out of the set, but you're seeing the different types of problems in progression. And then finally we say to her, what's 5/4 of 12? There are no Java bars being used. She says it's bigger, 15 units. Explain. I know that 3 times 4 would be 4/4. In other other words, if you think about the 4 through 12, you have 3 units of 4. And I'm sorry, 4 units of 3. And since it is 5, adding 3 to 12 will be 15. Since it's 5/4, I add a 4th, in other words, which means another 3 onto the 12 would be 15. What is the 3? Each 4th. And she added on there, but in subsequent problems we gave her bigger numbers so she didn't add on, and she was able to use multiplication to do that, and she could do essentially any problem of this type that we gave her at this point. So again, she used the activity originally of creating the fractional bar and then distributing the units across the parts. And ultimately, she was able to coordinate those 2 activities into one higher activity where there is no longer a need to do these sequentially, but she can just see the segmented quantity as one action. Okay. She still needs to compute it, obviously. So do you and I. But she doesn't need to separately create the 3/5 or whatever it is and then evaluate it. Now she can just see 3/5 of a unit. So this is what we're talking. This, in terms of the things I've said already, this is what we mean by a single abstraction. This is an example of how we generate a sequence that leads to the abstraction. Okay, and this is the way we think about it. I don't have time to go in a lot of depth on it. The idea of going from a sequence of activities to coordination of actions where you're no longer using your activities sequentially, but in fact those actions that make up the activity are now coordinated into a higher level action. Let me just see if there are any questions there before I go on to reversibility.
Were you claiming, I don't think you're claiming that the student isn't thinking kind of in 2 steps, divide by 5 and then multiply by 3.
No, that's the evaluation,
Yeah.
okay? That you know, we still need to, you and I still need to do that too,
Mm-hmm.
right? I don't know how to take 3/5 of something by itself. I mean, I can change it to a decimal and then I can do it, right? That's 2 steps too. But, you know, normally I would divide by 5, multiply by 3, or the other way around, let's say. I might know that. The 2 steps that I'm talking about her collapsing are the step of I have to cut up the bar and then think about and then distribute the original units in that bar. Okay? She now sees the quantity that she's taken a fraction of as being segmented, and she just needs to compute what that segmentation is. She doesn't need to separately. Remember, originally she didn't know what to do. It wasn't that she was doing 2 steps, multiplying, dividing and multiplying. She had no idea what to do. She needed to first cut up a bar, make 3/5, and then she needed to think about, okay, how do I figure out how much is in each 5th? Right? Now she doesn't need to go through those 2 steps. She sees that immediately as she has an image of what it means to have 3/5 of 20 or whatever it is.
So like the sequence has almost become anticipatory?
That's, well, I use anticipatory. So every abstraction has an anticipation. Those of you who know our work on participatory and anticipatory level concepts, the claim is only here that this is at the participatory level. That is, I didn't show you any evidence that on another day when she's not thinking about cutting up bars that she can call on this anticipation. Okay, that would be claiming that it was now an anticipatory level concept. I didn't show you any evidence of that. So I can tell you it did become anticipatory, but that's not what the claim is here. But it's a little bit of a problem with the language because every abstraction means that you now can anticipate something that before you would have had to carry out the activity to find out. Does that make sense? originally you needed to go through your activity sequence to get the result, and now you have an anticipation, not of the number result, but she can anticipate the result of making this fractional bar and then distributing the units. Okay, she now sees that as one thing. She can anticipate that this is what I get if I went through those two steps. Yeah, Jeremy.
I'm interested in, speaking of language, I'm interested that you call this a teaching experiment, because much of what you're doing excludes a lot of the things that people do when they teach. They explain, they give hints, they push in certain directions and so forth. This is more like an interview where you lay out the task for the person and ask them to explain, which is a kind of teaching, but it's a different sort of thing. I think teaching experiments somehow may give the wrong impression.
So let me explain that. So first of all, it's based on the idea of a teaching experiment as described, for example, by Les and Pat in the handbook, in which you have these cycles, right? Now, they don't say that they ask leading questions and so on, but in fact, if you watch their tape, they do. So what we're saying about it is we're using that same structure, but we've developed a very particular adaptation of it that has some very strict conditions on it, so that we can focus on just what we want to focus, which is on the activity and the reflection on the activity leading to the abstraction. So it's meant to describe how it builds off a teaching experiment and not emphasizing the teaching aspect of it. Yeah. All right, reversibility. So Piaget first talked about reversibility, and Steffi and Olive defined reversibility as taking the results of the scheme as input for producing a situation in the scheme. In plain language, it means, given the result, can you go back to what you started with? Okay? And anybody who's worked with kids in math knows that this is not automatic. Kids can get it one way, and then you give them the result and ask them to come up with what they started with, and they have no idea. And it's important at all levels of mathematics, whether it's addition and subtraction, a whole number, or calculus. We're continually trying to build conceptions that are reversible. So what we often see is curricula that develops two separate conceptions, the original conception and the reverse conception. So the most common would be teaching addition, and then based on the same manipulatives, we develop subtraction as takeaway or as comparison. Okay? We develop multiplication, and then we develop division in a parallel way to the way we developed multiplication. And so one of the effects of that is that students don't necessarily see the connection between those two. It's not that everybody who can do a multiplication problem and a division problem understands the relationship between multiplication and division. Okay, so you have the conception and the reverse conception. You don't have a reversible conception. When we think about developing reversibility, we're thinking about building the reverse conception from the initial conception. In other words, you should not have to go back. If I develop a conception through doing certain things in Java bars, I should not have to go back and do parallel kinds of things in Java bars to develop the reverse conception. I already have the conception. I should be able to now use that as the building block for building the reverse conception. Okay? So for us, if we have to go back to the same kind of ground floor level ideas or actions, we're not building the reverse conception on the conception. And the goal is that we're not only developing connections, we're developing a higher level conception because one is built on the other. We've used one in service of the other. And that's a more general principle for us in math education, which is that anytime you use a new conception as a building block for another conception, you're advancing students' understanding. Okay, being able to use a conception as an object that's part of another conception is a way of taking that further. So when we started messing around with this, we realized there's not a conception that represents the reverse of a conception. And we wound up with this typology that has multiple types. So first of all, to understand the way we're talking about it, we talk about the original conception, or talk about a set of conceptions in the following way. You have an input, you have a process that you do to the input, and that generates a result. Okay, so everything that I'm about to describe now is permutations of this idea. Right? So what we have here are 6 different types. This is our original, we're calling this the original conception. Okay? And then what we have is a conception in which you have the result, you have the input, you have to figure out what the process was. You have one where you have the process and the result, you have to figure out what the input was. Okay? So far we're still talking about the same process. Now you can also have the reverse process. I'm gonna illustrate all this, so it's a little abstract right now. And then you can go through the same thing with the reverse process. So for example, so we're treating multiplication as a non-symmetric operation now, okay? Because you get another whole set if you start reversing the factors, okay? But if you think about multiplication as I have an amount and then I iterate it, and so the input is the amount and the process is iterating it a certain number of times. Okay, so the initial amount is 2. I'm going to iterate it 3 times. I'm going to get 6. Okay, so this is your initial process. So then you can ask the question, how many times do I have to multiply? What do I have to do to 2 to get 6? Right, multiply it 3 times is the answer. And here, what would I multiply 3 times to get 6? 2 would be the answer. Sharing all my answers with you. I don't do this for everybody. And then we can have the reverse process. Okay? Now, the reverse process is interesting because in some areas we really need that reverse process. We don't just want people to think in terms of iteration. We also want people to think in terms of partitioning or quotitioning when we think about division. Okay, so in those cases, we want people to be able to think about the reverse operation. Now, the most common way we think about reversibility is going from 1 to 4. Okay, whereas here we have 2 times 3, 6, and here we have 6 divided by 3, 2. Okay, that's where we go from input and find the result, and here we have the result using the reverse process and finding the input. So as you can see, there are 6 different problem types that one can engage in here. And as we do our engineering for instruction, we're continually making choices, not only about these as possible goals, but also assembling these as possible trajectories. Okay? Which one which one would we do next? And which one is our ultimate goal? Is the goal this? Is the goal several of these? Is the goal this, etc.? Okay? Let me give you a...
Ari, would you repeat your description of number 2?
Sure.
I heard what you said, but I wondered if you meant it.
So, in terms of the multiplication division thing?
How did you describe that?
I said, what do I need to do to 2 to get 6? Okay?
Okay,
Now,
that I can follow.
okay? Because I'm asking about the process, and the process needs somebody to be able to come up with.
Before you said you multiplied it 3 times, and I couldn't figure that out.
No, I'm saying, yes, I'm saying the answer to that question is multiply it 3 times. That's the answer we're pointing at. I know it's not the only way to go from 2 to 6. Is that your point?
No,
Oh, okay.
if I multiplied 3 times, 2 times 2 times 2 is 8.
Oh, is that, I'm sorry, did I say that wrong? Multiplied by 3. Iterated 3 times.
So it's,
I'm using 2 different kinds of language and I conflated them. Iterated 3 times or multiply by 3. Yes. Thank you. Okay, so here's an example from our teaching experiments. So recursive partitioning, which is basically taking a unit fraction of a unit fraction. Okay, students don't necessarily know what 1/3 of a half is starting out. Okay, so if we take the original, if we start here, and we have a choice about where to start, but if we were to start there and say 1/3 partition into 2, we generate, and pulled one out. I didn't write in pulled one out, it gets too long there. And pulled one out, that would be 1/6. Okay? Then we could also say, what do I have to do to 1/3 to get 1/6? I have to partition into 2 and pull one out, right? I can say here, what fraction would I partition 2 times, pull one out, and get a 6? All right? That's all still with the forward process. Now, and then I can do the same thing with the reverse. To get, if I have a 6 and I iterate it twice, what do I get? Okay? If I have a 6 and I want to get 1/3, what do I do to the 1/6? And so on. Now, then the question also becomes, so what are our goals here? Well, a big part of our goals, we want them to know what they're going to get if they partition or they iterate. But we also are very interested in them knowing how to take 1/3 and make a 6th, or how to have a 6th and make a 1/3. Okay, and so we can use these both to specify what the goals are and to think about in what order do we want to try to promote these understandings. How will they build on each other? So this also is a tool for analysis in terms of being able to make sense of what kids do and don't do and can do and can't do. As I said, it specifies options for goals and affords building a trajectory. All right, I think I'm going to get this in if I do it quickly. So note the smaller type there. We've only worked in the domain of arithmetic, and what we're describing here is really about types 1 through 3. In other words, let me go back. So we're not worrying right now about the reverse process. Okay, forward process, we're talking about generating the result, generating the process, or generating the input. Okay, so what I'm going to talk about now basically is if you know this, how do you develop this and this? So this turns out, what I'm going to share, the technique is very simple. And so, you might say, So what? I think the explanation for why why it works is actually very interesting. Maybe you will, maybe you won't. There'll be more interesting speakers in the future. So here's the principle that we work with for being able to promote reversibility. One is when we're using learning through activity. That is, we're trying to use the students' understandings, their current activities that they have available to develop the new understanding. And we're in developing reversibility, as we talked about before, we're talking about constructing the reverse conception from the initial conception. Not going back to ground level, but using one to develop the other. So the idea is, can we use learning through activity to build reverse conceptions in terms of the way we're thinking about it? Probably can guess our answer. So I'm using this example because it's a little more complex than the examples I've shown you, but I think because it's more complex, one can appreciate more what's going on here. In other words, the need for it and the power of it. So the student has developed what we call case one of 4 cases of a missing value in equivalent fractions, which is they're going from smaller numerator and denominator to larger, smaller denominator, and the numerator is the one that's missing. And given that they have recursive partitioning, that's the easiest case for them. They can think about, if I took a 7th, I cut it up into 4 pieces. To get 28ths, I cut it up into 4 pieces. Okay, well, if I cut a 7 into 4 pieces, I'm going to get 4 28ths in each 7th. I had 3 7ths, so I'll have 12 28ths. Okay, and Kylie can do that and do that very proficiently at the point where we're starting this conversation. So we pose this. This is our case 2. Okay, so, and I'm giving you a scenario that represents the kind of thing that went on. This is not the exact data. So, let me go back. So she tries some different numbers there. She tries 10, and she'll say something. So if this is 10, I cut it each into 2. So I have each 5th is 2 tenths, and so I had 4. 2 times 4 is 8. No, that's not right. I didn't get 12. Let me try 25. 5. So it'd be cut each 5th into 5 parts. So I'd have each 5th would be 5 25ths. So 4 5ths would be 20. No, that's not right. Okay. So she's doing this kind of thing, and then all of a sudden she says, "It's 15. Yes, it's 15." Okay, and I'm using the way Kylie actually talks here. She gets very excited and leaves no doubt she's sure of it. And she explains that cutting the 5th into 3 pieces would make 15ths. There are 4 5ths, so there would be 12 15ths. And in subsequent tasks, she's now showing that she's able to do these problems. Now, she's essentially showing us how to promote it, which is that by trying values okay, what I want to say doesn't fit perfectly with the slide. By trying these values, her activity, now her activity is not using Java bars, right? It's not back to Java bars, okay, which is how she developed some of the original understandings. Her activity now is try a number and then use your case 1 reasoning, or essentially your case 1 reasoning that goes across the denominators to generate the numerator, and see if you generated the numerator that, instead of a missing numerator, is the numerator that you have, right? But it's the same reasoning she was using that when she was trying to find the missing numerator. Okay? So her activity now is try a value and use your case 1 reasoning and see if that works. That's the activity. Okay? And she makes an abstraction. She develops an anticipation from that activity, which she starts to know what's going to happen to this number such that she can anticipate what that value needs to be in order for it to work. Okay, so she's now developing that reverse understanding, which is, given what I have, what do I need to start with? Okay, and she's doing that from the activity of working with the original conception. The original conception right now is what she had for finding the missing numerator. So to summarize this, the use of the find the beginning state problem, okay, which is, we didn't just, well, I'll go back. I'll go to that later. So this kind of problem where she tries something and then verifies it, invokes the use of the conception she already has, okay, allows her to build on that. She checks using that original conception, and she comes to anticipate what she will do to the number to see the given result, so she knows the correct input. And one other point before I stop is that the modification of that we developed is to, sometimes we find that it's useful to have the student try particular values. So sometimes instead of letting them just try a value or guess at a value, we will say, would this work? Would this work? What would work? Okay, so it gives us some control of what they're trying, and so it's a way for us to have a little more control of the kinds of activities that are invoked. So, anyway, you know what I'm talking about.
I'm going to go back to the definition area of the questions. So I'm trying to make a sense of this from a science education perspective in the literature and science education. And from the get-go, in your line of research on learning with activity, what's your definition of activity? And as I hear this, it sounds like it could be learning through thinking, or it could be learning through...
So first of all, we're talking about mental and physical activity.
Okay.
There's just so far you can define this down, but basically what we define activity as short for goal-directed activity. We have a paper coming out on this. And when we're talking about an activity, well, let's do this way. Can you all see this board? Okay, so when we're talking about a learning situation, we're actually talking about somebody, generally we're talking about somebody doing a new task with their current level of understanding. Okay, that's what I mean by calling on activity you already have available. So that they set a goal for that task, and and they call on actions that they have available through prior conceptions. Okay, and they do them sequentially. That's the start of this process. And each of these you can think about, how do you show think about, in a cartoon? You can think about as being a conception in themselves. Actually, it's not the way we use the subscripts, but I won't go get this too complicated. As each of these is part of a conception which we think about as goal connected with action. So they've got a goal and they're able to do it without any learning by calling on activities they already have. And these could be mental or physical actions. And then eventually what we're talking about is that this A1, A2 gets coordinated into a new higher level action. We would talk about it this way, and then this is A1, so that the first, this is saying it's at the 0 level, this is at the 1 level. But basically trying to designate the fact that this is at a higher level than these. And that's what we mean by reflective abstraction. It's actually the work, as I mentioned before, it's the work on the participatory anticipatory that has pushed us to try to be very explicit about all of this and how to represent it in order to be able to create a clear explanation of what it means to go to the participatory and then from the participatory to the anticipatory. So the paper that's coming out is actually on the participatory to anticipatory, but has a whole big section first on work we've done on reflective abstraction in order to build that. Yep.
When you're talking about with the reversibility, I was wondering, when you talk about an initial conception, is there some kind of an imposed sequence that you're assuming, like partitive first or iterative first, or is it just whichever one was done first? Here's how you would get towards reversibility. Is it like
Yeah, so in a lot of situations, you have, you could teach either one. Now, for example, there's no reason you have to teach multiplication before division. You could teach division and then have multiplication be the reverse of division, right? That doesn't mean you might not have reasons for choosing one or the other, but there's nothing about the concept that says that one has to go before the other. And I don't want to ignore the fact that some people feel they're teaching them together, and I haven't had a chance to analyze those situations to figure out what we would say about it through our lens. But the interesting thing is, in doing the work we do, I hope you can appreciate, we set a very hard bar for ourselves, because the student needs to continue to make these abstractions from their activity. We're not going to tell them, we're not going to show them, we're not going to give them hints, and they're not going to hear any other kid who has ideas. Okay? So we have to continually figure out how to engineer for them to be able to make these abstractions. That's really hard. Okay? And we get stuck often. You know, we're just, oh God, I'm pacing around the office, you know, trying to figure out how do we solve this, you know? We're just stuck. And one of the solutions that has, one of the kinds of solutions we've typically come across is to teach, we're interested in a particular conception, teach the reverse, one of the reverses of that conception first, and then develop reversibility for it to get to the one we want. Okay? And we didn't go in understanding that that was a way to design. We kind of learned through experience that we could do that. That, in fact, often the reversed conception, the one we wound up using first, was something we were not interested in. But it was a really useful stepping stone to the to the one we were shooting for, which we couldn't figure any way to get to directly. So it's fun when you realize those things. Did I answer your question?
Sure, thanks.
Yes.
Okay, so while you were going through with this discussion about this one student was thinking, and I'm thinking of, okay, you're doing a learning activity where you're focused on this one student. Are you going through this with the idea that somehow you can, after you have found out how this one student thinks, then you are able to use this with other students?
It's a good question. So, altogether in this project, 2, 4. Basically, there are 5 students who we collected significant data from. The general idea is that, and this is very much tied to my idea of learning trajectories or learning progressions, which is that there are no unique learning trajectories. There's no such thing as a learning progression, that is the way kids learn. All progressions are relative to the kinds of experiences you've provided for those kids. And in lots of cases, you can turn a lot of trajectories on their heads if you give them different instruction. And we were particularly aware of that because we started out this project by analyzing the Okonjo-Davidov curriculum, which does some things in the first grade that people would say, no, you can't do that till middle school. So the idea that there's one trajectory is a very dangerous idea. So if we understand that, then what are we doing? What we're trying to do is create powerful trajectories, at least a powerful trajectory. And so every student we work with gives us clues as to what that might be. In other words, if you can build this out of this, and this out of this, and this out of this, that could potentially be useful for a lot of students. Okay? And what happens is then you work with another student, and you find out the things that you haven't successfully engineered. You don't see a student who says, no, that whole trajectory is a bad idea. That's not a result you can get when you're working that way. But what you can find out is, no, where Kylie was able to go to from point A to point B, the student can't go from point A to point B. So what did you leave not engineered? What are the kinds of adaptations you have to make in anticipation of students who can't go from point A to point B? Can you build into your trajectory the ability to bring along those students who don't readily go from point A to point B? Does that make sense? Somewhat. You want to ask a follow-up question?
I do apologize, but we are out of time.
I thought we were going to 11:15. I'm sorry. I would have left more time.
No, we only have an hour. But,
Okay.
If anybody, that 15 minutes is for more one-on-one, if anybody would like to speak to you personally.
Okay.
I appreciate everybody coming out and giving a round of applause for